Hi everybody. I thought I'd just make a quick video solution for week 6 homework. So I will be grading very generously since I'm providing this solution. And anyway, I hope it helps you. So let me just go through the problems. First of all, problem chapter 12, number 40 is R a subring of the 2x2 matrices with integer entries. So I took a look at this and I was like, wait a minute, no, it's certainly not a ring because the identity matrix is not in there, right? Like 1, 0, 0, 1 is not in there. But then I was scratching my head and going, oh, that's right. Galen has the definition of a ring without identity as his default, which I don't care for, but you know, hey, I haven't written an award-winning abstract algebra book either, so what do I know? But anyway, so he's working with the definition of ring which doesn't demand an identity, so we can't rule it out by just saying there's no identity. We need to check closure under subtraction. That checks. If I take two matrices of this type and I subtract them, that checks. But when I multiply them, it's like, oh, wait a minute, that's not the right pattern because you can see pretty clearly that this and that, they're not the same animal. It's more apparent when you FOIL it out. So clearly R is not closed under multiplication, thus R is not a subring, at least with respect to the usual matrix multiplication of 2x2 matrices. And then I went looking for a specific example to buttress my claim, and I thought, well, I'll try 1, 2, 2, 1, and multiply it. And then I multiplied it, and I'm like, oh man, 4, 4, and 4, so those match up, despite the pattern that they don't generally match up, right? But this is also a good counterexample because for it to be this pattern, I should have that the sum of the diagonals, like the 1, 1 and the 2, 2, it should be equal to the 1, 2 or the 2, 1. And that just ain't the case here because 5 plus 5 is 10, and 10 is not equal to 4, right? So anyway, the multiplication fails. That's why it's not a subring. Now problem 62, these solutions I'm showing you here, they're not perfect, but they're, you know, I decided not let perfect be the enemy of good. I think these are pretty good solutions. You're like, you probably take a point off it with mine, and you're probably right. Sorry. Let's see here. You know, my advisor told me that if you don't take points, well, he always told me that if you didn't take points off, it wasn't grading. So I guess he instilled that in me. But anyway, so this is Q adjoin the square root of D. Now, I don't think he says it, but customarily D is square free in this kind of application. Obviously, if D is like 25, this is just dumb, right? Because like the square root of 25 is 5. Q adjoin 5, which is just Q again. All right, so we really want to look at the case there D is not a square. All right, and I don't believe Galen says that in the problem, but whatever. Now, first of all, it's a subset of the reals, so we're going to look at it. We're going to try to see it's a subring of the reals, right? Because since it's a subset of the reals, we automatically know that addition, multiplication satisfy the ring axioms in the sense that it's associative and that sort of thing. The real question is it actually closed under, you know, negation, addition, multiplication, that stuff. So we're going to apply the subring test to this set, looking at it as a subring of R. And so we can do that, and here's the real calculation down here. The difference of two such elements is again such an element, and the product of two such elements is again such an element. And so, hooray, well, now we've got the Q adjoin square root of D as a ring, rather a subring of R. Now, to show that it's a field, which is what we're trying to do here, right? We need to show that every non-zero element has a multiplicative inverse. And the proof of that is right here. It's just really just a straight calculation. This is the calculation we were all taught in, like, I don't know, junior high school or high school algebra, right? Multiply by the conjugate. And that's the secret sauce here, because this, you know, this multiplicative inverse is given. So this is a real number, which we have a sense of, right? And that real number can be rewritten like this, at which point you can say, aha, it's a rational number plus another rational number times the square root of D, which means it's in this character right here. And so apparently the multiplicative inverse is again in here, which means that every non-zero element of this guy is a unit, has a multiplicative inverse. However, not so fast flag on the play. How do I know that this is non-zero? Well, I need that that's non-zero, but notice that that being 0 is equivalent to d being the quotient of a squared over b squared. And so if I take the square root of this, it gives me square root of d is the absolute value of a over b, which would be a rational number, and then that would contradict the assumption that d is square free. So now I'm being a little bit glib here. You could be more careful here. You could dig down into the substructure of the primes and so forth and give a more a complete argument there, but that's essentially the heart of it. I mean, the details which I've omitted are essentially the details that are needed to say prove the square root of 2 is irrational. So here's number 63 in Z5x, polynomials with coefficients in Z5. If we look at the ideal generated by x squared plus x plus 2, right, find the multiplicative inverse in the quotient, polynomial quotient by I. In particular, find the multiplicative inverse of 2x plus 3. All right, so first thing I do is free myself of this notation because it's really a drag. And I like to use the notation alpha is equal to x plus I. Sometimes I'll use an x bar rather than alpha, but you know, whatever. I've been trying to use alpha in all my conversations with you guys lately, so let's stick with that. And so the key is, in this quotient, you're setting I as I behaves as the 0, right? So long and short of it is that if you define alpha as such, then alpha will get to satisfy the conditions which, you know, define the ideal. Namely that alpha squared plus alpha plus 2 is equal to 0. Right? In other words, that's equal to the ideal, which is the 0. Right? Now, I really shouldn't say x squared plus x plus 2 equal to 0 because that's not my right. X squared plus x plus 2 is a polynomial in Z5. It's not a, you know, equivalence class of polynomials, which is what's in the quotient, right? So we should be careful about this sort of thing because that's kind of like the whole you know, the lion's share of what the problem's about. So it's good to have a notation which distinguishes between alpha and x, and that's, well, here it is. All right, so since this is order 2, we know that that means that we can squash all polynomials of higher order and just keep truncating them down, 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 down until we only have a linear polynomial left as our representative. So it's not hard to see that the quotient space of this by a quadratic ideal is a plus b alpha. Now I have theorems stating such in the notes. I want to say it's like lecture 29 or something like that in the 2018 notes, but this is nevertheless the case. Even if you didn't have my notes, it's not hard to convince yourself of this. So what we're trying to do is we're trying to solve the equation 2 alpha plus 3 equals to thing we don't know, which has the form a plus b alpha equals to 1. And so how to solve this? Well, we should keep in mind alpha squared is minus 2 minus alpha. And so what I did is I just multiply this guy out like so, and I apply the condition that alpha squared is minus 2 minus alpha. And the other theorem that we know is that 1 and alpha are linearly independent over Z5. So if I have an equation where I have something and then something else multiplied by alpha, I have, just like with a complex number, I have the real and the imaginary parts are separately, independently linked to the right-hand side versus left-hand side of the equation. Same thing's true here, but I get a pair of Z5 equations in this context. I need 3a minus 4b equals to 1, and I need this coefficient right here to be equal to 0. Now notice that the minus 2 plus 3 is just plus b. All right, so lo and behold, yes, Benjamin?
Can I take a shower?
Can you take a shower? Well, I suppose you can. Go on in there. Sorry, guys. Slight interruption, but do not unplug my thing, please. I've got my my lamps here plugged into the outlet in the bathroom because the other outlets are used up with other things. My apologies in advance. My 6-year-old tends to sing in the shower, so this is going to be interesting. Could you keep it quiet, Benjamin? Okay, thank you. All right, so getting back on track here. I'm kind of making a video here right now. I need to focus. Okay, thanks, buddy. All right, so like I was saying, we've got these pair of C5 equations we need to solve. And it just so happens that these ones can be solved by direct substitution, right? Because this one says that b is minus 2a, so that I can plug it into the first equation. Excuse me, that gives me 11a, which is, by the way, the same as a, because 10 is equal to 0 in this context, because we're working over z5. So 11a is equal to a is equal to 1. So apparently a is equal to 1, and once I know a is equal to 1, then b is equal to minus 2, which, by the way, is equal to 3, because 5 is 0 here, all right? So lo and behold, the multiplicative inverse of 2x plus 3 plus I is equal to 1 plus 3x plus I. Now, I said, okay, well, I'm gonna check my answer because, you know, I don't want to lose any points. And also just to be safe, because let's see here. So anyway, so I multiply this by that, going back to the cumbersome plus I notation rather than the alpha notation just for a second. And when I do that, I get this times this, multiplying that out, because that's how we multiply cosets, right? We multiply representatives. That's well defined because, again, it's an ideal, so that's what we need. We need to be looking at cosets of an ideal so that the factor group is well defined, but it is here because the group structure here is an additive group structure, so all subgroups of an additive group are normal, hence the factor group that we form in the ring is, well, it's fine. Anyway, so that multiply these representatives, I get my 6x squared plus 11x plus 3, but I'm working mod 5, so that's x squared plus x plus 3, but notice that x squared plus x plus 2 is 0 in this context, so that simplifies back down to 1 plus I, which is exactly what I want because 1 plus I is the additive, excuse me, it's the multiplicative identity and the polynomial, or the quotient ring here. And so there you go. That's the multiplicative inverse is that. Now, of course, yours might look different. You could, like, you know, it could be, if you had 1 minus 2x, you'd still be right. If you had, you know, minus 4 plus 3x, you'd still be right. I always have to be careful when, if I'm grading these, to be watching a watchful eye for the Z5 ambiguity, you know, because your answers could look different. All right, problem 64 here is this one. And here we were asked to show that these two rings were isomorphic, all right? And so on the one hand, you've got these particular subset of real numbers of the form a plus b root 2 with integer coefficients. On the other hand, you got this set of 2 by 2 matrices of this form right here. Now, so I don't think this was supplied, I just made it up. I mean, what else are you going to do? So, creative leap, phi of a plus b root 2 is equal to a 2b b a. You can prove that it's additive, in other words, that phi of a sum of two things is the sum of the phis. I didn't write that down because I was lazy. I'm sorry about that. I hope you can forgive me. The more interesting part is the oh, wait a minute, I did write it down. I was harder working yesterday, apparently. I've already forgotten. So, phi of some of these two things is that, which is that, which is that, which is that. So it's additive. And then multiplicative as well, because if you do multiply two typical elements, and I'm being bad here. I really should, of course, say let this and that be an element of z root 2, and consider, I'm missing some language here, which I fuss about you guys for not writing down. So my apologies. This was originally intended as an internal document, but I decided to share it with you guys instead. So, so here we go. Multiply those out, you get this, but then the mapping definition of phi says put this thing here, and do twice the coefficient of root 2 here, and put that there again, and then, okay, so great. On the other hand, I can multiply these like so, and I get that. And then you tilt your head, squint, compare, and they're equal. Therefore, phi preserves both addition and multiplication. That means phi is a homomorphism of rings. And if I was not so lazy, we could also show phi is a bijection. So the complete solution also needs to show that phi is both one-to-one and onto. But both of those are pretty easy to show here because it's kind of obvious that it is. I mean, you can easily write the inverse of phi, right? If I take phi inverse of this, I get a plus b root 2. So like, if you can write down the inverse, it's obviously injective. But indeed, this is an isomorphism. All right, the next one, this is like a pretty famous problem. Like, you know, in a world, in the world of if I had to survey, you know, like 10 modern or abstract algebra classes, and I was to, you know, take a look at the questions that were put in homework and tests, and I was to see a common question that was, you know, in all of the classes, this would be in there. You know, this is a very, very famous and standard problem. Suppose you have a ring with x squared equals to x for all x in R. Prove R is commutative. So you can go round and round and round in circles to this forever and ever. If you do not use the distributive property, you will get nowhere. But if you do the distributive property on like x plus y squared, that pretty quickly gets you to the fact that xy plus yx is equal to 0. And then I'm like, okay, well, I know I need, see, that's not quite what I want. I want to have xy is equal to yx, right? So I'm like, well, let's try x minus y squared. I do that, and that yields for me that x minus this plus y is equal to 0, which then canceling the x, and this is 0, right, by our work in the previous step there. So that implies to me that y is equal to minus y. Oh, well, if y is equal to minus y, then we're done. See, because xy plus yx equal to 0 means xy is equal to minus yx. But hey, that's equal to yx. So there you go. I've just shown you that an arbitrary, if we pick any two arbitrary elements in the ring, by this algebra right here, it follows that xy is equal to yx. Now, my bad, I would fuss at you guys. I'd take off something. If I wrote it like this and I was you, you should start by saying let x and y be elements in the ring, and then give these arguments, right? And so anyway, let me just fuss a little bit about my lack of verbosity here. This is actually an interesting thing. You can then start looking at things. How about like you have a ring where x cubed is equal to x? Or what about the ring with x to the 4th equal to x? Categorize all such rings. I believe these questions were exhaustively studied by the mathematician Jacobson, Nathaniel Jacobson, I think he is. The perhaps most awesome student to ever come out of the University of Alabama, of all places. Now, if you ask people in Tuscaloosa who's the greatest math student ever to come out of the University of Alabama, they wouldn't know. But if you asked them who the current football quarterback is, I'm sure they could tell you. So anyway, I lived in Alabama for a year and a half, or two years, yeah, so I should know. Anyway, football aside, problem 66 is actually very simple. Also a very nice test question, I would add, because it's just so simple. An idempotent of a ring in an element E, but it's got so many nice ideas, is an element such that E squared is equal to E. So let R be an integral domain. What's that mean? It means that means it's a commutative ring with no zero divisors, right? So if we have E squared equals to E, well, that gives us E squared minus E is equal to 0. But then we can factor that, like so, in the commutative ring, right, where the usual laws of algebra hold. And well, if that's equal to 0, that means either E is equal to 0 or E minus 1 is equal to 0, in which case we either have E is 0 or E is 1. And that was what we were asked to prove, that if you have an idempotent in a ring, in an integral domain, it's necessarily the case that the idempotent is either 0 or 1. And there it is. Well, that was pretty easy. Now, problem 67 is a little bit more open-ended. It's kind of an adventurous problem of sorts, because you're asked to decide whether or not these operations that you're given here form a ring. And I'm kind of tempted at the start of all this to say, yeah, maybe they do, because, you know, union and intersection are associative. That's a good sign, right? Because the multiplication and the, addition being associative is kind of a good sign. Certainly the addition's commutative, right? A union B is B union A. And then I got to thinking, okay, so what about identity? Now, I guess you don't have to have a multiplicative identity in Galeon's definition for a ring, so that's not a deal breaker, but you do have to have a 0. Everybody agrees that there's got to be a 0. So here, if you think about it for a bit, you'll realize the empty set. And this right here, guys, is my notation for the power set of I. This is the set of all empty and non-empty subsets of I. So that right there includes the empty set and a lot more. And so if you look at the union of A with the empty set or the empty set with A, either way you slice it, you get A back again, right? So it looks like the empty set serves as the additive identity, the 0 for this potential ring. And also the whole set would serve like the multiplicative identity, because anything you intersect with the whole set, it gives you back the set again, the subset again. Oh, word salad. So like, oh, well, maybe this works. So then I thought, well, okay, what's the negative? What's the negation under addition of the set? So then you're asking the question, what set can I take the union of A with to get back the empty set? And at that point I realized, oh, it's hopeless. Nope, that will not do it. So in fact, no, I do not believe this is a ring. I don't see any way you can fix the additive inverse problem. Now, is that a proof? Not really. I mean, so this is a really kind of, in some sense, it's a kind of nasty problem, because to prove something that, well, I guess I've proposed the operation, so I guess it's not so bad. But I don't know. Maybe you could improve on my proof that there is no set. It's not a ring. But that's how I see it. Now there is a way to get a ring structure on the power set of a set, but it's not with just union intersection. I think it's with the symmetric difference, if I recall correctly. It actually defines something called a Boolean ring. The Boolean rings, an example of that would be that one we had in the last one where x squared was equal to x. That's an example of a Boolean ring, like in honor of George Boole, founder of logic and stuff like that. Now here, Z4i, here we're looking at a plus bi, where the coefficients are from Z4, I squared is -1. Find the units. So we're trying to figure out when can we solve this equation. And so if you multiply that out, that means we're trying to solve ax minus by equals to 1, and also bx plus ay equals to 0. And so I looked at that, and I rewrote it as a 2x2 matrix equation, and I did the math. Now, more on this math in just a second. This is the 2x2 matrix inverse. What you do is you've flip the diagonals, which is kind of hard to notice here, right? Flip the diagonals and put minuses on the off diagonals, which is easier to see, all right? And then this is the 1 over the determinant, which in this context you should understand is multiplication by the multiplicative inverse of the determinant, which is the a squared plus b squared here. So anyway, we find that the inverse exists in Z4 only if, well, the inverse of this guy, it exists in Z4 if and only if a squared plus b squared inverse in Z4 exists. So when is this invertible? Well, in Z4, the units are 1 and 3, right? 0 and 2 are not invertible, because 2 times 2 is 0, which means 2 can't have an inverse. 0 divisors are not units. Units are not 0 divisors. Those are disjoint categories. Anyway, so the question is, a squared plus b squared equals to 1 or 3. Well, if you think about it, you're going to either be able to achieve that with plus or minus 1 and 0, or 0 plus or minus 1. Also plus or minus 2 plus or minus 1 gives you 5, which is 1 in this context, and likewise plus or minus 1 plus or minus 2. All of these different cases give you an invertible numbers in here. This number system, right? This number system is not a field. It has many numbers which don't have multiplicative inverses and yet are non-zero. But this, I believe, it has 16 numbers in it. All right, 16 numbers in it. Many of which are units, but a few are not. In particular, plus or minus 2, plus or minus 2i, and like plus or minus 1, plus or minus I, where the pluses and minuses are any which way you want, because any way you slice it, that gives you a sum of squares being 2, which means that this formula doesn't have a solution. And so, you know, putting it together, it's really not very surprising you could have probably figured this out without the matrix calculation that I just showed you there. See, because A plus BI inverse is actually this, and so, which is really just, if you look at it, it's the usual, it's the usual complex thing, right? Like, essentially it's just this 1 over, and this is a subset of complex, well, it's not a subset of complex numbers, I should say. This is, so this here, I'll put some quotes around that, as that's not quite standard notation, but it really does work out like this, a minus bi over, a squared plus b squared. So it really does appear like you just multiply by the conjugate over the conjugate. All right, so there's that. Now, just one more thing before I forget, because I said I should tell you guys this. If you want to calculate, if I can find a marker here. So if you're calculating A, B, C, D inverse, right? And this formula I'm going to show you here, this is true in any commutative ring, certainly, all right? So certainly if you have entries from a field, but this is just as good if you're taking, say, entries from Zn. The formula is this: AD minus BC. I take that number, I have to find the multiplicative inverse of it, and then I flip the diagonals, like so, and I put minuses on the off diagonals. Now, I always show this in my lectures, but I couldn't find it in my notes, so I thought I should share that with you. So this is, of course, the determinant right here, right? So the long and short of it is A, B, C, D, right, is an element of the units of the, the 2 by 2 matrices over the ring R, if and only if the determinant of the matrix is actually an element of the units of the ring. So let's see here, for example, if I'm working over, let's say, Z6, right? And I have the matrix, 3, 4, 1, 0. Just made it up. I have no idea what's going to happen. Then the question is, does the inverse exist? Well, let me quick calculate it. 3 times the determinant of this is 0 minus 4, and so the answer is does not exist, because the determinant of 3, 4, 1, 0 is minus 4, which is, by the way, equals to 2, which is not an element of the group of units of order 6, right? Now, on the other hand, if I had 3, 4, 1, 1, then that inverse would exist, because this has determinant 3 minus 4, which is minus 1. Minus 1 is always a unit. So like, what is in U6? U6 has the numbers relatively prime to 6. It's got 1, no 2, no 3, no 4, just 5. That's kind of lonesome in there, just 1 and 5. So this has determinant minus 1, which is also known as 5. So, okay, so the determinant is, like I said, so I do minus 1, multiplicative inverse of that, flip the diagonals, minus is on the off diagonal. That's the multiplicative inverse here. Now, let's clean it up a bit, right? So that is, what was the inverse of minus 1? Well, it's minus 1, because minus 1 times minus 1 is 1. So I got 1, minus 4, minus 1, 3. Multiply that through, I've got minus 1, 1, 4, minus 3. Great. And there you go. Of course, we could clean that up a bit. We could write that instead as like 5, 4, 1, 3, if you want to write it in terms of positive representatives or residues. But there you go. This is how you find the multiplicative inverse in Zn over Zn, just like that. And then there are other questions you can ask here, like you could look at the additive order versus the multiplicative order of the matrix. The additive order would be how many times do you have to add it to itself before you get back to 0. The multiplicative order would be how many times do you have to power it till you get to the identity matrix, or, well, I guess it doesn't have to go to that, does it? Well, this one does, because it's invertible. But anyway, those are also interesting calculations. You can look at powers and products of these. All right, enough about that. Let's go on. So let's see here. I already told you about that one. Problem Problem 69. Show that R is a commutative ring with unity. Define the principal ideal generated by A to be like it usually is. Prove it's an ideal. Well, it's good. If I'm calling it a principal ideal, it better be an ideal. So, all right, so let X be in the ring and consider Y as an element of this. Then Y, of course, is equal to RA, hence X times Y is equal to X times R times A, but we're in a commutative ring, right? So I can rewrite, well, anyway, just by associativity. I don't even need commutativity at the moment. So I have X times R times A, which is, that's a ring element times A, therefore it's in this. And also if we look at the difference of two things in the ideal generated by A, it's kind of bad form to call it ideal while you're trying to prove it's an ideal, but anyway, if you look at two things in the set generated by A, then the difference is again a ring multiple of A, and therefore is in the set generated by A. So we also know that XR is equal to RX. So however you slice it, it's closed under multiplication by the ring, and it's a subring. So altogether, it's an ideal. So I'm using the ideal test if you want me to be more careful here. Problem 70, I said to find a quotient ring which constructs the complex number system. The simple and direct answer there is just real polynomials mod that. There you go. That is the complex number system. And here, understand that I is actually the is like alpha in my earlier discussion. It's X plus the ideal. All right. Problem 71. Excuse me. Find the maximal ideal of this. So the key idea about maximal ideals in rings is that if it is a maximal ideal and we quotient by it, we should get a field, right? In contrast, if it's a prime ideal and we take a quotient by a prime ideal, we get a integral domain. So things to keep in mind. So R mod I is a field if and only if I is maximal. And also another fun fact to know about, the Z mod P is a field if and only if P is prime. Okay, so I went hunting. I said, okay, well, how about if I take Z8 and I mod by the set generated by 4 or the set generated by 5. So this is 2 things, this is 6 things, and so that leaves me with 4 cosets, or 6 or 5 cosets rather. So that's kind of funny. It works out to Z4 cross Z5. That's isomorphic since 4 and 5 are relatively prime. This is isomorphic to Z20, which is not a field. All right. So therefore, this I, not maximal. And then I tried. Well, I thought, well, I'll try 2 and 5, and that gives me Z2 cross Z5, which is Z10. Again, not a field, right? I will well. And it's not even an integral domain, right? Because there's 0 divisors in here. So this I and that I are neither maximal nor prime. On the other hand, if we take the ideal Z8 cross Z5 cross the principal, the ideal generated by 5 like this, then that gets me, this is 0, 0 cross Z5 is just Z5, and that's a field. Therefore, I is maximal, and here's the other maximal ideal. Like that. I believe those are the only ones. So I think I got everything on camera here. Finally, problem 72 is a kind of twisted version of a standard problem. And so you're given a nilpotent element of order n, or it doesn't have to be order n, that it's 0 at order n. Maybe order n minus 1 is not non-zero. I don't know what nilpotent order it actually has. It doesn't really matter. And you got a unit. And so we're trying to find what is the multiplicative inverse of 1 over u minus a. I give you the hint of the geometric series. And so what I'm intending there, and it's a kind of sneaky trick, is to factor the u out like this. So if I factor u out like that means I have to put a u inverse there. And then, so this should be like u inverse over that. And then geometric series says it's the constant times 1 plus the radius squared plus dot dot dot. Identifying the constant here is the inverse of u, and the radius, or I should say the ratio of the geometric series is a u inverse. Now this is all just formal nonsense, but we suspect that that the inverse for u minus a is given by that, if the geometric series is any guide. So to check if it works, we just need to multiply, right? So I've got my guess, now we can check it. And in fact it works. Because you get kind of a telescoping, you get the u times all this stuff, then minus the a times all this stuff, and it conspires in such a way that the u inverses match up, the powers of the u inverses match up, and the powers of the a match up, with pluses and minuses canceling, until finally the last term that you're left with is a to the n, u to the inverse to the n power, but that's 0 because you're given the a to n is equal to 0. In other words, the geometric series truncates like you'd like, and the initial term is u inverse, which is 1. So there you have it, proof positive, it is invertible. Now that would be a very unfriendly test question, unless you'd seen it before in homework, in which case it would just be, hey, did you do your homework test question? And those are the kind of questions we do tend to give in online classes, since you guys have your homework to look at during the test. Yeah, you know. All right. And let's see here. See if I have anything to tell you about week 7. I'll just show you a little bit of week 7 while we're at it here. So here's problem 75. To show that this is irreducible, it's a quadratic, right? So if you can show it has no zeros, that proves irreducibility. We have a theorem. And so how do you show there's no zeros over Z11? Well, check them. So you got 11, you just plug them in. Hey, no zeros. So it's irreducible. Happy day. Now, problem 76 is a little bit more adventurous. You're supposed to write f of x as a product of irreducibles. So there, what I do is I just start plugging numbers in. If I find something 0, then that tells me there's a factor by the factor theorem. So I factor it out, all right? And it's like I factored an x minus 1 out. I did a little bit of math to figure out how to factors. Maybe you could just see it anyway. X minus 1 times x squared plus x minus 6. And then, of course, this also factors, right? And I saw that by just plugging numbers in. Like I plugged 0 into it, I plugged 1 into it, I plugged 2 into it. I was like, oh, ooh, I got 0. That means that this is not irreducible. If it's got a 0, it's not irreducible. It can be reduced. So the factor theorem told me that there was an x minus 2 there. Once I knew there was an x minus 2 there, then it made me just go, oh, duh, of course, that's x plus 2 times x minus 2 times x plus 3, obviously. And the thing is, once you've got it factored into linear polynomials, well, game over, you're done. So there's that problem. Let's show you that one. Let's see here, what else can I tell you? I'll let you guys think about 77. 78's not really that bad either. 73, let me just talk about 73 briefly here. So you can, check about, yeah, I mean, it's a homomorphism. The more interesting thing, of course, is that the kernel, it looks like this, right? Well, that's not really the interesting part. The interesting part, of course, is that since the homomorphism is a surjection, the first isomorphism theorem gives you that R mod the kernel is isomorphic to the image, and so that makes part D pretty easy to answer. And also notice that we can get that the kernel is a prime ideal because Z, of course, is an integral domain, like I was just telling you about quotient by prime ideal gives you integral domain, if and only if, right? And you can see that the kernel is not maximal since the quotient by the kernel is equal to, my bad, I think I was out of frame there, sorry about that. Since the, sorry about that. So the kernel is not maximal because R mod the kernel is the integers as we just discussed, so that's not a field, which means that it's not maximal because an ideal is maximal if and only if the quotient by the ideal is a field in the context of a commutative ring with identity. All right. And then one last thing, and I'll stop this video. Problem 77 is what I was currently fiddling around with, but let me just show you how I work this kind of problem. So Hopefully I won't get stuck. You're supposed to find the multiplicative inverse of a plus bx in here. So my opening move is to make a notation which is more convenient to my purposes. In this case, alpha is x plus that, right? Oh, actually this one is, well, I mean, fine, but I wish I had a harder problem in front of us. All right, so what this gives us, of course, is that alpha squared minus 2 is equal to 0, right? Let's see here. What am I? Oh, I'm trying to find the multiplicative inverse of that, though not. All right, so it's okay. So alpha squared is equal to 2. We'll keep that in mind. All right. So we're looking at a plus b alpha. That's what that looks like in our alpha notation. We're trying to find c and d such that we get 1, right? So you multiply this out, you got ac plus bd alpha squared plus ad plus bc times alpha equals to 1. Now alpha squared was equal to 2, right? So we've got ac plus 2bd plus ad plus bc times alpha, equals to 1. So this gives me two equations. It gives me, on the one hand, ac plus 2bd equals to 1, and also ad plus bc equal to 0, because there's no alpha on the other side. So this is equating the coefficient of 1. This is like equating the coefficients of alpha on both sides. This one's actually kind of hard to do in this way. Wouldn't you know it, I get stuck on something at the end of this video here. Oh, man. Well, I know the answer. Fine. All right, well, this is kind of going nowhere at the moment, but you could solve these equations. This works out better for other examples, not this one as much, I guess. So we could look at it this way. So essentially, like morally, if you like, in that sort of strange sense of the use of the word, alpha is essentially like the square root of 2, right? So we're essentially asking the question, like, what's 1 over, a plus b root 2, right? So, well, the same trick that we saw earlier. Sorry if I was out of frame. So if we multiply by the conjugate, right, then everything should be hunky-dory, if you believe in that sort of thing. So we've got a minus b root 2 divided by a squared minus 2b squared. If we believe this, this suggests that we should try c equal to a over a squared minus 2b squared, and d equal to minus b over a squared minus 2b squared, right? And we can check if this right here and that right here solve these equations up here, right? Because if they do, then we're definitely in business. Let's see here. So let me try that out. So we've got a times c. I'll just check one of them. So c was a over a squared minus 2b squared plus 2bd. So we've got plus 2b my d is minus b over a squared minus 2b squared, right? So what's that give us? That gives us a squared minus 2b squared over a squared minus 2b squared, which is, lo and behold, equal to 1. Woohoo! Right? And I guess it's actually fairly apparent that the other equation works as well, right? So, all right, let me work one more example here just to try to help you guys out. So like, don't let these problems psych you out. These problems are not hard. If you're asked to, you know, for example, you could be working in the ring, which is something like, oh, I don't know, z7 of x mod, let me just make something up, x to the 4th plus x cubed, oh, I don't know, plus 2x plus 3. There, that's weird enough. And then the question is to find, you know, the alpha inverse, where alpha is equal to x plus this guy. That was supposed to be a 4. All right. So let me share with you the secret sauce here. So it's really not bad. So in this quotient, right, in R, what we have is we have alpha to the 4th plus alpha cubed plus 2 alpha plus 3 is equal to 0. So look at this a different way. What that is alpha to the 4th plus alpha cubed plus 2 alpha equals to minus 3, right? And I'll trade that minus 3 for a 4. All right. Then what? We'll factor alpha out. So we've got alpha times alpha cubed plus alpha squared plus 2 equals to 4. All right, what's the multiplicative inverse of 4 in Z7? Let me think about it for a second. 2. 2 times 4 is equal to 8, which is equal to 1. So 4 inverse is equal to 2 in Z7. All right. So if I multiply this equation by 2, I get alpha times 2 alpha cubed plus 2 alpha squared plus 4 parentheses is equal to 2 times 4, which is equal to 1. And we're done. Therefore, alpha inverse is apparently just 2 alpha cubed plus 2 alpha squared plus 4. So that's it. You know, it's not, these problems are not as bad as they appear at first glance. I mean, anyway, that's kind of it. Anyway, that's all I got for you guys today, so I hope that helps. Thanks.